Groundwater is the water present beneath Earth's surface in soil pore spaces and in the fractures of rock formations. A unit of rock or an unconsolidated deposit is called an aquifer when it can yield a usable quantity of water. The depth at which soil pore spaces or fractures and voids in rock become completely saturated with water is called the water table. Groundwater is recharged from and eventually flows to the surface naturally. Natural discharge often occurs at springs and seeps and can form oases or wetlands. Groundwater is also often withdrawn for agricultural, municipal and industrial use by constructing and operating extraction wells. The study of the distribution and movement of groundwater is hydrogeology, also called groundwater hydrology. Let us start with the importance of groundwater measurement. Now basically, the monitoring of groundwater levels continually is an essential element of any effort to integrate groundwater science with water management decisions. It provides important data serving as a key input into the decision-making process concerning spatial planning and climate change adaptation. One measurement is no measurement. Measurements are required continuously for a reliable policy decision. By monitoring the groundwater continuously, you can monitor the long-term sustainability of an aquifer as a safe and stable water supply. You can manage groundwater levels and prevent damage by salt water intrusion and drought or flooding. Then, the groundwater monitoring network provides the data based on which measures can be designed to issue drought or flood warnings timely and take appropriate mitigation measures. It also suggests when to change the settings of your water management system and adapt to the climate change. A good measuring program should comprise of a wide range of observation wells, frequent and longer periods of measurement of groundwater levels, and accurate data collection. The amount of fresh water available on the globe is limited, and hence it will be useful to understand how the water is circulated in the earth and atmosphere cyclically. The hydrological cycle would illustrate this phenomenon. So, we go ahead to understand about the hydrologic cycle. The hydrologic cycle describes the continuous movement of water on, above, and below the surface of the earth. This cycle begins with the evaporation, that is, when water from Earth's soil, plants, and water bodies turns into water vapor. As moist air is lifted, it cools, and water vapor condenses to form clouds. This is called condensation. The vapors in the clouds condense until they form water droplets, and it rains, that is, rain. The moisture is transported around the globe until it returns to the surface as precipitation, such as rain, hail, sleet, and snow. Once the water reaches the ground, two processes occur. Some of the water may evaporate back into the atmosphere, and some water will flow along the surface of the land and enters surface water like lakes, rivers and streams, and is carried back to the oceans as runoff. The rest of it penetrates the surface and percolates into the soil. It is called recharge. The water then moves down through the soil as groundwater and is stored in the aquifer below. Once the water has joined the aquifer, it doesn't stop there. The groundwater slowly moves through the spaces and cracks between the soil particles on its journey to lower elevations. This movement of water underground is called groundwater flow. Let us go through another important aspect called discharge. Eventually, after years of underground movement, groundwater comes to a discharge area where it enters a lake or stream and becomes surface water. There, the water will once again be evaporated and the cycle begins again. Water has been transported through the water cycle for millions of years and will continue to do so forever. Now we go ahead with the world's freshwater scenario and importance of groundwater. Almost all of Earth's water is saline and is found in the oceans. Of the small amount, 2.5%, that is actually fresh water, only a relatively small portion is available to sustain human, plant and animal life. The globe image represents how much actual water exists compared to the total size of the Earth. Notice the blue portions representing water. They look small because they are being compared to the size of the whole globe. The image shows that Earth's water resides in a very thin slice all around the Earth's surface. Distribution of Earth's water. The middle bar shows the breakdown of fresh water. Almost all of it is locked up in ice and in the ground. Only a little more than 1.2% of all fresh water is surface water, which serves most of life's needs. The right bar shows the breakdown of surface fresh water. Most of this water is locked up in ice, and another 20.9% is found in lakes. Rivers make up 0.49% of surface fresh water. Although rivers account for only a small amount of fresh water, this is where humans get a large portion of their water from. Central Water and Power Research Station (CWPRS) proposes to establish a testing, calibration and certifying facility (TCCF) for groundwater level measuring sensors under a variety of hydraulic conditions at CWPRS. Under National Hydrology Project, the sensors shall be procured by various implementing agencies, IAs, for use in their respective areas of operation for an automatic water level monitoring system. Automatic water level recording systems are extensively used for monitoring levels of regional groundwater regime, for monitoring of a regional groundwater system from central location. Automatic water level monitoring systems can be programmed to make measurements in observation wells at a specified frequency over long periods of time. Hydrographs, thus constructed, can be used to accurately identify the effects of various stresses on the aquifer system, with space and time providing the most accurate estimates of fluctuations. The system consists of a fluid pressure sensor connected through a cable to an automatic data logger with the provision of data retrieval, transmission, and online web data monitoring. The need of testing facility system. The automatic water level monitoring systems need to be programmed to make measurements in bore wells at a specified frequency over long periods of time, as these measurements are the principal source of information. Long-term systematic measurements provide essential data which is needed to evaluate changes in the resource over time, develop models for management, and to achieve it, it requires suitable sensors as well as an automated monitoring system. Similarly, we also look into the groundwater level measurement methods. There are varieties of groundwater level measuring methods such as steel tape, electric water level sounder, and pressure transducers, etc. The steel tape method. The graduated steel tape method is easy to use and is considered to be the most acceptable method for measuring the water level in non-flowing wells of moderate depth. However, it may be impossible to get reliable results if water is dripping into the well or condensing on the well casing. Also, the method is not recommended for measuring pumping levels in wells. Here, rugged steel tape for measuring groundwater level in the borewell is used for comparing the results of the sensors. The electronic water level sounder. Electronic water level sounder gives alarm or light when the tip of the tape touches the water in the borewell and gives exact water level in the borewell. The electronic water level sounder method is used when water is dripping into the well or condensing on the inside of casing walls. Wells are being pumped and a series of measurements are needed in quick succession, such as in aquifer tests. The groundwater level sensors. A hydrostatic level probe typically uses pressure sensor to measure the water level. The main component of a pressure sensor is the sensing diaphragm, which converts the difference in pressure between either sides of the diaphragm into a measured signal. The front of the diaphragm measures the water level pressure, hydrostatic pressure, plus the barometric air pressure pushing down on the water. The groundwater level sensors with vent. Vented loggers include a built-in vent tube that enables the loggers to automatically compensate for atmospheric pressure changes. By equalizing these changes on both sides of the pressure sensor, a well-designed and maintained vented water level logger can provide high-accuracy water level data. While vented loggers have the potential to provide great accuracy, they also have a number of limitations that can cause problems and result in bad data or data loss. These limitations include Most vented loggers require the use of desiccants for moisture protection, which increases the amount of maintenance. The groundwater level sensors without vent. Non-vented loggers are barometrically compensated using a barometric pressure logger and a simple software function to perform the mathematics. Barometric pressure values can also be obtained from weather stations within a 10-mile radius. The laboratory setup for the testing of the groundwater level sensors should have environmental chamber. The performance of the groundwater level sensors made up of electronic components varies under varied temperature, pressure and humidity conditions. There is a need of testing these groundwater level sensors at different environmental conditions in order to check vendors' desired specifications. Sensor performance needs to be effectively evaluated for their durability, longevity and fouling by placing them in the conditions in which they will be used. This can be accomplished through Environmental Chambers (EVC) facility. The sensors themselves also need to be tested in uncontrolled environmental conditions. The test tank. The sensors can be checked in a transparent tank which is used to test the response of the sensors by varying water levels in tank with a scale for visual observations. Performance of the sensor will be observed by placing the pre-calibrated master sensor and the sensor that is to be tested at the bottom of the tank and varying water column up and down gradually with small increments. The bore well. The sensors shall be tested in the real-time field environment in a bore well. The sensor shall be lowered inside at different depths in the bore well of 6-inch diameter grilled by CGWB near TCCF Center inside CWPRS campus. The readings given by the sensor shall be compared with the actual depth measurement carried out by a sounder and/or steel tape. Even though we have the best laboratory setup, we need to take proper precautionary measures while handling the sensors. We should keep watch on the surroundings side of sensor installation, especially trees, as they grow and may have shadow on the solar panels. You may have to change the location of solar panels. If any heavy electrical machinery installation is nearby, then use appropriate device to stabilize the power supply. Always carry block diagram of the system and manuals. Check cables and connectors, antenna, battery and power supply. Check all indicator lamps on, off according to the manual. Check GSM, GPRS signal availability. You should not tamper with any switches, knobs if you do not know its function. Do not disturb any wire connections without consulting the service engineer. Do not touch open wires or half-open connectors. That may be hazardous. Do not disturb any knobs on instruments. These may be zero settings or voltage input-output settings. That will change data values and will take long time to find the fault.